happens if you fall into a black hole?
The results are very interesting. The experimental results, it's a confirmation of something that the majority of loop quantum gravity community expected on theoretical reasons. We see the black holes. We see the matter falling in, right? We see the spiraling the accretion disk, as they call it. And we know, because we know general relativity, that matter, it's spiraling and then going into the horizon. And we know general relativity, so it goes into what we call the singularity. What happened next to that matter?
Carlo Rovelli, welcome back. It's been 2 years, and I'm extremely happy to be speaking with you again.
Thank you very much, Curt. It's a great pleasure being here with you again.
So, as you know, there's some recent results, I believe from China, that people present as a death blow to loop quantum gravity. What are those results, and do you agree with this assessment?
The results are very interesting. The experimental results, they have not been presented a death blow to loop quantum gravity by the authors of those results, not at all. And they're not a death blow to loop quantum gravity at all. In fact, the opposite. It's a confirmation of something that the majority of loop quantum gravity community expected on theoretical reasons. But they do disprove some suggestions that were done about 15 years ago of something that, if happened, would have been great, a way to confirm the theory, which unfortunately is not there.
Okay, so what is that?
So the situation is the following. Some time ago, there was a suggestion by Lee Smolin and some collaborators of him that perhaps there could be a way of finding a trace of quantum gravity in some signals coming from very far away from the in the universe, some light pulses, some very short pulses of light that we get from very far away. And the idea was the following. It was a beautiful idea, in fact. I got very excited when it came out. The idea is that quantum gravity in general, quantum theories of gravity, tend to predict that there is a minimal length. There is a structure of space at some length. Now,
what's important here is that it's a minimal spatial length and not a minimal space-time length or space-time volume.
Yes, very good, Curt. There is a minimal spatial length. So if you measure something, you can measure a certain length, a shorter length, but there's a minimal one, a minimal non-zero one. You can measure zero, of course, but you can measure a minimal non-zero one. Now, if you take this naively, you can make a consideration which it's very tempting. And the consideration is the following. All right, so this means that space is like a grid with a minimal length. Now, we know that on grids with a certain spacing, light does not behave like light in vacuum, but behave in a more rich way in the following sense. In vacuum, all the colors of light fly at the same speed, the speed of light. But if there's a grid, the high frequency color are sort of slowed down.
Why?
Because they interact with the grid itself. So the equation of at some point light, if it is sufficiently small wavelength, high frequency, so the color it's appropriate. Light has doesn't move in a uniform space, move in a granular space, and this affects the propagation of light and slows down high frequency more than short frequencies. This is well known. I mean, there's a reason for which light in water goes a different speed that lies in vacuum. Light interact with the material in which it is. So when we say that light goes always the same speed, we mean if there's nothing interference, if there's no structure, no granular, no matter, in light goes the speed of light, but in the presence of something, light slows down, so to say. And so the idea was, okay, so quantum gravity says that at a very, very teeny small scale, there is some structure, and therefore we should see this dependence of the speed of light from the color. That was the idea. It's a very tempting idea because you can put numbers in. You know the length at which you expect the space to become granular, and therefore you
So this was a quantitative prediction. It's not just qualitative in the way that you're explaining it here.
No, it was a quantitative. That's what made it interesting. Because if you want, it's easy to do a calculation of how a certain grid, the certain grid with a certain spacing of certain length of the elementary steps, how it can affect light, which frequency would affect. So we know the size of the granular structure of space, so to say. So people would, Smolin in particular, had this great idea. Say, wonderful. I mean, perhaps this might affect the speed of light. Now, there's a very, very teeny change of velocity, of course, because the dimension of the grain are very, very small. But that's a key idea. If you have light traveling for very, very long distances, a teeny difference piles up.
Right.
Because some rays goes a little bit faster than the others, so they come up separated. And since the universe is nice and gives us some explosive phenomena very, very far away, and we see pulses of light come from this explosive phenomena, some supernova, some very intense explosion, the other corner of the universe, the light that gets to us, if what I've said is correct, should arrive, some wavelength, some color should arrive before some other color. So we should see a delay in the pulses that arrive to us. Some frequency arrive before, some frequency arrive later.
And in that case, what's important is not only the distance, but also that what's being sent is a high energy photon, and then also so a mixture, high energy and low energy.
What is important is that what we receive is not a photon of a single energy or a group of photons of a single energy, but is a pulse of different energies. So we have energy means frequency for light. So we have some light of different colors, if you want, some more red, some more blue. Some high frequency, some short frequency. And by resolving them, which is easy, that's what optics instruments do, if this is correct, we should have seen these pulses to arrive expanded in colors. So first to arrive, say, the red, and then to arrive the blue. A nice phenomenon, namely the arrival of distant signals of different colors at slightly different times is what has been disproven by the recent result. And so the recent result, basically, they observed some signals coming from far away, and they checked that at the level of precision where was expected this phenomenon to happen, the phenomenon does not happen. So that phenomenon was a hope to see a granularity of space, but it doesn't happen. Now, I haven't yet answered your question, Curt. Why this is not a problem for loop quantum gravity? The answer is that at the time, many years ago, when this phenomenon was suggested by Smolin, a lot of people, including myself, got very excited. So said, okay, so Lee has this intuitive picture of what could happen. Does it happen for real in loop quantum gravity? And very soon, a number of papers appeared, including a paper by mine, that convinced the community that no, that's not going to happen. This phenomenon that Lee suggests, it's not predicted by loop quantum gravity, and the reason is that the kind of discreteness predicted by loop quantum gravity is not at all. The idea is not at all that space is like a grid. Space is not like a grid. If it was a grid, it would be a classical grid, not a quantum phenomenon. And it would contradict a property that it's a property of the theory, which is invariance and the Lorentz transformation, invariance and the symmetry of special relativity. Now, the theory is invariant under Lorentz transformations, and this phenomenon breaks Lorentz invariance, so it cannot be predicted by the theory. Now, this is beautiful because it's really a quantum phenomenon, and that's why people get confused about that. Now, quantum mechanics allows precisely symmetry and discreteness to happen together. It would not be possible classically. Let me give you an example, because I think, or a couple of examples, because these are,
Sure.
I think that they explain. One is that when in quantum mechanics, we all know when we study quantum mechanics, the original thing is that if you measure some angular momentum, the how things rotate, or the angular velocity of something, this is quantized. That's one of the quintessential quantum phenomena. So you only measure certain values, certain discrete values. Now, in classical theory, if the angular momentum was quantized, it meant that along some variable, some directions, things could turn only at certain velocity and not at other velocity. But of course, imagine that you have a body that turns around this axis at a certain velocity. If you look at it rotated, with respect to the new axis, the component of the angular momentum is just a little bit smaller. Not much. You reduce it, okay?
Mm-hmm.
And therefore, from a rotated frame, you would not see the angular momentum quantized. You could change the value of the angular momentum continuously.
Right. If you're allowed to rotate continuously.
If you were allowed to rotate continuously. So that seems to say that it's impossible to have angular momentum quantized and rotational invariance. But that's wrong, because in quantum mechanics, we have angular momentum quantized and rotational invariance. How come? Well, what happened is that when you measure the angular momentum in one direction and in another direction, the two operations do not commute. So if you measure one, when you measure the other one, you don't have a precise value. You have a probability distribution of values. You can have a probability to measure the same, or one smaller, or one larger, right? So what changes continuous is a probability distribution, while what you actually measure, it's only those particular values. So one should be very careful, because
Right.
the fact that length is quantized in quantum gravity does not mean that, however, does not mean that you're breaking any invariance of the theory. It only means that if you go there and make a measurement, you get a finite result. If you had it measured from a different Lorentz frame, you would have obtained the same result. Another way of thinking about that is the following. Imagine you take the standard model or any quantum field theory. We know that even in the vacuum, if you measure in a small region, it's a quantum effect, you find particles, right? That's the so-called virtual particles. It's a physical fact. If I go in a small region and check if there are particles, I find them, even in the vacuum. Because it's only if I measure in large region that is vacuum. Now, one could reason, and that would be the mistake, if light travels in the vacuum, okay, if the frequency is high, it would see a small region, so it would see this virtual particles.
The virtual particles, even without loop quantum gravity.
Even without loop quantum gravity, and therefore it would slow down, because we know that light slows down if there's matter around, okay? So therefore, in standard quantum field theory, high energy, high frequency light should go slower, But it doesn't. It's not true. It's not correct. And it couldn't, because the theory is it's Lorentz invariant, and in Lorentz invariant theory, light in vacuum goes at the speed of light. So the mistake is to take too literally the granularity of space predicted by quantum gravity. And it's beautiful. Quantum gravity doesn't say that space is granular. Quantum gravity says that if you make a small measurement, you see a minimum length. Okay? This is like quantum field theory. Quantum field theory doesn't say that the space is full of particle, the vacuum is full of particle. It says that if you make a measurement in the small, you see particle. It's very different things. Light can travel in a vacuum of quantum field theory without seeing anything. But if you make a measurement, you see particles. So similarly, light travels at the speed of light in a loop quantum gravity background space or quantum background space. But then if you go there and make a measurement, you cannot go smaller than something. So this was realized long ago. There was a lot of discussion at the time, many papers, quantum gravity and Lorentz invariance, minimal length and Lorentz invariance. It was clarified. And the loop quantum gravity community was disappointed at the time, because somehow theoretically the window, the possibility of seeing quantum gravity phenomena would have been great. I was very excited at that. That's why I started looking at it. But the theoretical analysis, the theoretical calculation showed, okay, this effect is not going to happen. Time passes, the experimental do the experiment, the observational, the people in astronomy do this measurement. They confirm the fact on which the loop quantum gravity community had agreed that if the theory is correct, this phenomenon should not happen. So everything is fine. It's, if you want, it's disappointed. It would have been better if we had but everything is fine for the theory. Now, unfortunately, let me put it this way. The experimental were completely clear in the paper. They said if a theory predicts granularity, there's a problem for that theory. But they never obviously said this is a problem for loop quantum gravity. In fact, if you want, even in string theory, there were papers that suggested a similar phenomenon for string theory. But nobody, in fact, in the astronomers' paper, they quote various people that had suggested similar phenomena in loop quantum gravity, string theory, but
right.
Never there was a clear result that string theory predict that. And therefore, the fact that it doesn't happen is not a problem for string theory. Similarly, never there was a clear argument that implied that the phenomena come from loop quantum gravity. Now, unfortunately, not from the scientific community, but from external commentators who like to make everything polemical, a big. The old papers by Lee suggesting that this could happen were resurrected and presented as, you see, there is a prediction for quantum gravity. Was disappointed, but I don't think this is serious.
Okay, going back to the reason why in quantum field theory you should not expect a variable speed of light dependent on frequency. You said that it's only when you measure a small distance that you get these virtual particles. But isn't it technically if you measure any distance, you get virtual particles? They're just of different energies, like infrared?
If you measure any distance, you're right. But when you measure large distances, if you want, so to say, the number of virtual particle goes down. So to see virtual particles, you have to go into small. Otherwise, they are there, but they are less and less. The probability of seeing them goes to zero continuously, but goes to zero.
So for a high energy photon, why isn't it acting like it's measuring at any given point? Like what constitutes that measurement?
That's a very good question. That's a very good question. It isn't. You go into the question of the theory, it isn't. That's a very good question, because somehow once we get to the idea of the virtual particle, we use it. We use it intuitively, but we should be careful because virtual particles are not real particles. We have this idea, virtual particle just dancing around, so the vacuum is a sea of oscillating things.
Yes, just like we talked about science commentators, there's also some science communicators, and they show those animations of a jittery space-time, and it makes people say, wow, that's so cool, bro.
It's so cool, but it shouldn't be taken too literally. That's often the problem with quantum mechanics. It's counterintuitive. So you try to make it intuitive, which expresses some aspect, but the analogy is not good, so it doesn't express other objects. For instance, the vacuum of quantum field theory, in some sense, it is full of virtual particles, but as a state, it doesn't change with time. It's stationary. Nothing moves. So this image of everything moving fast is, in a sense, is completely wrong because it's a stationary state. It's a solution of the Schrödinger equation where nothing changes. In elementary quantum mechanics, we say that a harmonic oscillator has a ground state, and this ground state is a Gaussian mathematically. In the ground state, the oscillator is in the minimal of the energy, but with some probability distribution. Okay, and the state never changes. It's just that. If you let it untouched, it stays that. Now, if you look where the particle is, if you try to pinpoint the particle, which is a vacuum state, you don't find a zero. There is a probability you find here, you find it there, because that's a spread, the quantum spread of the state. So it's true that if you look, you find it somewhere. Then you look again, you find it somewhere else. Then you look again, you find it somewhere else. Even if you try not to disturb too much, which is hard, you have this spread, okay? But this doesn't mean that there's a jumping particle there. There's a state which doesn't move. The source of the confusion is that we're not talking about particles, okay? We're talking about quantum objects, which are not particles. So a quantum space-time is not a discrete space-time.
Right.
It's a quantum space-time. To say that a quantum space-time is a discrete space-time is the same misunderstanding as saying that a quantum particle is a particle that dances there is here and there.
When people talk about quantum fields, they often, to the lay public, give this idea of a temperature field is usually the first analogy. And then they give this idea that it's something akin to an ocean and then there's ripples. But technically speaking, in quantum field theory, it's not a field in the same way that we think of a temperature field. It's an operator-valued distribution. Precisely. So they're operators. Is there something else that's going on with the discretization of space in loop quantum gravity that is akin to, well, it's actually operator-valued discretization or something like that?
Yeah, to say that something, it's an operator, it's some variable, it's given by an operator, is precisely to say this variable is a quantum variable, right? This is a mathematical translation of the same thing. And to be a quantum variable, it means that the system doesn't, there is a sense in which the system doesn't have a specific value of that variable, but has, you could talk about a probability distribution of that variable. Well, there's a quantum probability distribution. It doesn't mean that it can be either here or there. It means when it interacts, you can find it here and there. So that's what we call quantum superposition. I mean, when we say a particle is in a quantum superposition, can be here or there, it means if you look, you find it here or you find it there. But you shouldn't think that it's here and there because the two can interfere. So if you think that it's here or there, you make a mistake about your prediction of the future. So in a sense, it's here and there at the same time. or more precisely, you can only say that if you interact with the thing, you find it here and there. But if you want to see what's going to happen later, you have to still consider both possibilities. So that's a quantum superposition. Good. So now if you have a field, like the electric field, or the magnetic field, or the electromagnetic field, quantum field have to be thought as a superposition of different field configurations. So sort of a wave function or cloud in the space of possible fields, in the space of possible configurations of the field. So the electric field is neither here like that, nor like that, nor that like that, but is a little bit of those, and the quantum state gives a probability to each one of those. When you go to quantum gravity, gravity, that's what we learned from Einstein, is a geometry of space. There's a very visual possibility that gravity is just space bending. Good. Beautiful. So in quantum gravity, the geometry of space is not determinate. It's a superposition of different geometries. So here around us, space is roughly flat. Minkowski space is a flat space. But if we keep into account quantum gravity, in the small, it's a quantum superposition of all possible fluctuations. And in this quantum superposition, light can still travel at the speed of light. But if you go into small and bingo, you want to solve what is the geometry here, you find a geometry which is neither this nor that. You find a geometry which have limitations in length. So there's no structure smaller than a certain length.
Yes. Now, when someone's in high school and they learn about gravity, they learn it's a force, and then some clever undergraduate says, actually, it's the curvature of space-time, and then some clever graduate student says, actually, it can be torsion, and then some PhD may say, well, it could be non-metricity or torsion or any combination of that and curvature. Does loop quantum gravity make a definitive statement as to whether gravity is curvature, torsion, non-metricity, or some combination of them?
Great question, Curt. Let me answer in steps. First step, you go to high school and they tell you that gravity is a force. Okay, the sun and the moon, the sun and the earth pull one another with a force which act at a distance. Be careful. Is that false? Or is that right? I believe that's right. That's not false. It's just approximate. It's an approximate description of reality. Okay? If I say, I look there and I see a forest, and you come to me and you say, no, Carlo, you're wrong. It's not a forest. It's a lot of trees with leaves and so on and so forth. I say, okay, I mean, you have a better description, but it's still a forest. Okay?
Yeah.
So once you learn general relativity, you learn that there's a better description. Why better? Because the other description doesn't capture some phenomenon, it's approximate. Okay? So there's a better description in terms of curvature, but in the common situation in which you are, you can still talk about force. It's not wrong to talk about force. It's just proper names for something that happened when you don't look too in detail. That's the first point. So, could we say that Newton's theory is an approximation and general relativity is a true story? I know, of course, because we know there is quantum gravity. So, Newton's theory is some approximation. Einstein gravity, it's a much better description of reality. Quantum gravity is going to be a better description of reality. Is that going to be the last ultimate description of reality? No, come on. Your program is titled Theory of Everything, which is great, but I don't believe we are any close to any theory of everything. Plenty of things we don't know. We don't know what is dark matter. We don't know what is...
It better be, otherwise I'm out of a job shortly.
Exactly. So I believe that your show can go on for long time before we could ever think about the theory of everything. If we get there, we'll talk about, but we're not there by very far. So every theory, it's a way of describing the world at some level of precision. Okay, it's not one right, one wrong. Okay, having clarified all that, which I think is important because it's not often said, and because we used to say, it's wrong that space-time is flat. It's not wrong. It's true. It's just not very precise. Around here, space-time is flat. Okay, to all degree I can measure it, is flat. So I'm saying something very right. And if you say, well, but if you measure it even better, it wouldn't be flat. True. But to the extent I can measure it, is flat. So I'm saying something right. There is a force pulling down. If I let my hand fall, it by force pull down, it's true. Can you say it's false? No, it's true. Okay. So having clarified that, I come back to your question.
Okay.
In general relativity, in the context of general relativity, space-time, gravity is due to curvature. No torsion, no metricity, nothing like that. There are attempts to rewrite generativity, in fact, is possible, or extensions of generativity with some more geometrical, different geometrical, more rich or different geometrical. Nothing, as far as I know, that I've given a lot of, that has had a lot of success that allows us to understand better. If you go to loop quantum gravity, gravity is not just curvature. It's certainly not no metricity. It's quantum curvature. So gravity is a geometry which is curved, so it's curvature. But in addition, it can be, as I was saying before, in a superposition of different curvatures. So you don't really change the geometrical language that you use it, but you allow it to be quantum, namely you allow reality to be in a quantum superposition of different geometries. So if loop quantum gravity is correct, the best way of thinking about gravity is that, look, if quantum mechanics is correct, the best way of thinking about a particle is still a particle, but it can be spread. It can be in a superposition of here and there. And that's the wave function. So if loop quantum gravity is correct, you can still think a gravity, a geometry, but this geometry is spread. So you have a quantum superposition of geometry, the wave functions of the geometries.
Have any people gotten so far as to do interpretations of loop quantum gravity in the same way there are interpretations of quantum mechanics? So some may say that the wave function is some pilot, and then the particle is just riding atop that pilot. Are there any loop quantum gravitists that would say, well, the curvature is somehow riding atop some pilot curvature?
Yes, there are. In fact, there are exactly papers that do what you just said. The quantum gravity is still a quantum theory. So all the mysterious aspects of quantum theory are inherited by loop quantum gravity. So if you want to interpret the quantum theory, make sense to it, which I think is not a bad idea to go into this exercise, there are various ways of interpreting quantum theory. One is the one you just mentioned, the other is many-world, the other is relational quantum mechanics, which I've worked a lot.
Right.
And each one of these can be applied to loop quantum gravity. So if you want, you can be a loop quantum gravity many-world guy, a loop quantum gravity relational quantum mechanics. It seems to me that the relational way comes more naturally. In November next month, I'm going to a philosophy department to give a series of lectures in which that will be one of the main topics. Princeton, I'm invited 1 month in Princeton to give a series of lectures, and I'm gonna talk about how to interpret, how to make sense of quantum mechanics, keeping in mind that quantum mechanics should include also quantum gravity. So the interpretation of problems which are open in quantum gravity that reflect the interpretation of problems which are open in quantum mechanics.
So can you explain, just give a brief outline of what relational quantum mechanics is, and then also explain what it's like to articulate an interpretation of quantum mechanics? Because many people, as they're showering or they're driving, as they're going about their day, they're like, I have an interpretation of quantum mechanics. But is there something that's more symbolic or more quantitative, more rigorous, more precise, more stringent than just surmising on your own about the interpretations of quantum mechanics?
Interpretation of quantum mechanics is thinking how the universe may work. If quantum mechanics is true, if the prediction of quantum mechanics are true. The point is that if you take a shower, you come out with an idea, and you start telling it around, very soon somebody would tell you, but look, think carefully. If what you say is correct, then this and this and this. And you say, yeah, you're right, it doesn't work. So most way of thinking either don't work or force us to some very unexpected consequence. So the discussion about the interpretation of quantum mechanics is a discussion about these consequences and this strangeness. When I make a measurement, okay, I have a particle, and then I split with a Stern-Gerlach apparatus, and then I see whether it's here or there. So I've measured the spin of the particle, and can be one direction or the other. This is a thing that can be done in a laboratory. Every grad student can go in laboratory physics and do this measurement, and then something strange happens. Because quantum theory doesn't really tell you what's going on. It tells you only you have a probability of seeing this or probability of seeing that. Now, there are various ways of thinking about that. One way, for instance, is that, there is much more than what the theory is telling you. The theory is telling you that this wave, this superposition, but as you were saying, in addition, there is also a true particle that is riding the wave and going here and there, which we didn't know where it was exactly before. So you add a lot of extra equations to the theory, extra variables, which we don't see, but are supposed to make sense of what is going on. Okay, some people say, why do you want to add plenty of things which you never use? Other people say, that's a different interpretation of quantum mechanics. It's not really that either one thing happened or the other thing. Both things happen. You see one thing happen because you yourself become two. There's one you that sees up, one you that sees down, and there's never a moment in which something strange happened that the particle is here or there. The particle is still in both places, but you also become in both places. So there's one you that sees up, one you that sees down. Okay, that takes away some problems. Then we have to think, Curt, that you and I are just one version of zillions of copies of us that are doing other things, and so on. So whatever you try to do, you have to clash something harder to digest. Is this an empty conversation? No, I don't think so, because I think through this conversation we're going to get some clarity how to think about quantum mechanics. When Newton did his... Newton and Galileo and Huygens and Kepler and everybody else got to Newtonian mechanics, it was a long discussion because people would say, well, wait a moment, can I say something is moving or not? In Newtonian mechanics, you cannot. There's no meaning in saying something is moving or not. You can only say something is moving with respect to another thing or not. Okay? That's incredibly strange. It is strange, but we have digested it. We have digested exactly what we have learned. We have learned that there is no meaning in being still versus moving unless it's referred to some object. And so it was a strange message we have understood about the world. Now it's clear. We haven't yet understood what is a strange message about the world that has come with quantum mechanics, I believe. I have my own way of viewing. I'm convinced of my own, but until it becomes common, it's not an answer.
People who are proponents of the many world will say that what they're doing is following the math. They'll say this phrase, quote unquote, like, we take Schrodinger's equation seriously. But yet yours is an alternative that doesn't do away with Schrodinger. So are they incorrect in saying that they're just following the math? They're actually following the math plus putting an interpretation on? Or is it true that you can, from the math, infer the interpretation of many worlds?
I don't think they're exactly correct. They do mean something. They're not stupid. They have a way of thinking. They're very smart people out there. But I think it's not exactly correct that they follow the math for the following reason. If you go to school and follow a good class in quantum mechanics, at some point you get a clean math, okay? And the math, it's essentially the Schrödinger equation plus the operators plus the eigenvalue, eigenvector construction that give the probabilities of seeing one thing and the other. So the math has various parts. What they do is trying to do the following. Forget this, just keep this and follow the math and see if you can get the other one. So they make a choice. They make a choice at the beginning of the mathematical book, the so-called postulates of quantum mechanics. They discard the projection postulate, they discard the measurement postulate, they discard the eigenvalue postulate, and they just keep the quantum state and the way it evolves. And they say, this is a true math. But I wouldn't say that this is a true math. I would say that the relevant math is the rest.
Interesting.
Yeah. So what they say is that they take away a part of the mathematics of the way it's commonly presented, and they try to recover it just from the first bit. To some extent they do, but with a very long and complicated story and a lot of this complicated idea that implies that in some sense you and I are just one of many copies. So you have to accept something very strange about reality if you go that way. The idea that this part of the math, it's not true quantum mechanics. It's a strange idea. It's not. It's choice of how to try to make sense about that.
Going back to the Chinese experiment, did they outrule even something like Wolfram's model, which is about space-time atoms, or do they just put a bound?
Oh, that's a good question. I actually don't know. I should. They definitely rule out certain things. I mean, in fact, many things. Any naive idea of that, quantum gravity, most people would agree, gives a finite length. Okay, the question is how this finite length it's actually coming in nature. They rule out the idea that this finite length is actually a finite grid in space. That's out. It would definitely give this effect,
right?
And the effect is not there. I would suspect that it could be used to rule out any theory which is non-quantum. So Wolfram theory, in a sense, want to derive quantum from something else, and there is a granularity which is classical. So it might be that gives a problem to that theory, but I'm not sure because I've not looked into the details. And you asked, it's just putting a bound on it. I
can't see why it wouldn't just put a bound.
Look, theoretical physics is less clean than the way it's usually sold. you can always change parameters and save yourself. Theories are not really ruled out by. It's very rare that theories are ruled out by just an experiment or a group of experiments. Theory usually come with flexibility, or theoreticians can add flexibility, and so new experiments you can just patch up your theory. The point is that
Yes. In the loop quantum gravity case, it's not flexibility that is evading this experiment.
right, that's correct.
It's that loop quantum gravity didn't predict what they're saying it predicted to begin with.
That's correct. That's correct. Right. So what commonly happens is that some measurements are hard to fit into a theory, harder and harder, and at some point you say, no, come on. Look, take Newton's theory, right? Where did Newton's theory go wrong? Newton's theory go wrong in Mercury. Mercury essentially doesn't do ellipses. The ellipsis turns, the perihelion of the ellipsis turn in a way that doesn't fit with Newton's theory. That's a fact, we know. And in fact, general relativity accounts for this shift of the perihelion Mercurium perfectly. That's marvelous well. But when it was measured, did people say, oh, that kills Newton's theory? No. People say, oh yeah, but maybe the sun is not really a sphere. Maybe there's another little planet inside, Vulcan, that gives this effect.
Or there's another planet, yeah.
Maybe this, maybe that. They were all open options. So it didn't kill Newton's theory. It's just, was a trouble for Newton's theory. It had to do funny things to fit it. And when general relativity came out and gave bingo, exactly the right number in such a beautiful, marvelous, clean way, people say, oh no, that has to be a better explanation.
So why do you think these polemical commentators, as you put it, are so eager to say there's a death blow to loop quantum gravity?
I think the polemic between loop quantum gravity, string theory, sells a lot. People get excited. Look, this is winning, this is losing. And of course, if you can say something strong like that, it looks raising a polemic, and it looks science it's slow. It's a lot of debates. Things are not clear. It takes time. It's not about big emotions. I mean, sometimes there are big emotions. I mean, the fact that everybody expected supersymmetry was not found was a big shock for the community. I mean, there were articles written by scientists in some Le Monde, the French journal, saying, "Oh, it's a big crisis for physics." But even there, does this rule out string theory? No, of course it doesn't. It's not that because there were no. Because string theory doesn't really uniquely predict low energy supersymmetry. As I said,
right.
I think commenting about science, it's rarely commenting about clear-cut things. And in this case, I don't know. I mean, I don't know exactly what has happened, but there have been a little bit of acrimony between strings and loops, which is stupid, I think. We just don't know. I mean, we should, each one of us, ending the discussion is good to say, look, you're wrong here, you're wrong here. That's how the discussion, but definitely nobody's dead. No theory is dead. And we all wish things went faster, but science has never been fast. Fundamental science has never been fast. It takes decades.
You wish things went faster except the high energy photons.
That's correct. Absolutely.
Okay. Then the counter argument that I've read in the comments from some of the commentators and some of the comments themselves say, okay, well then that either means that loop quantum gravity was disproven or that it's untestable. But it sounds to me like what you're saying is that it's either disproven or this wasn't a test for it, not that this is untestable.
Absolutely correct. That was not a test for it since the very beginning. I mean, there had been a discussion a theoretical discussion within the community, and the outcome was clear. No, this is not a test of the theory. People are working hard for finding tests of the theory, or at least measurement that could help support the theory or help take away credibility in the theory. So there's a lot of, that's what many people in loop quantum gravity are doing right now.
I have a quote from Sabine Hassenfelder from the video that I sent you, and she said that the smallest possible area, which we talked about, is not compatible with Einstein's theory, and you need to modify Einstein's theory to do that. And if you do, you'll find that the speed of light is not constant.
Yeah.
So that was the argument of Smolin back then. And then she said the opposite was vocally represented by Carlo Rovelli, who said, no, we can recover the symmetries of Einstein by averaging over all possible ways to take space apart into areas.
Right.
And yes, I think you can do that. This is her now. But in this case, you effectively get back areas of zero size because there will always be some observer for whom area is arbitrarily small, and you go back to the problem with singularities that loop quantum gravity was trying to avoid. So basically, you can't have your cake and eat it too. And I'm curious what your response is to that.
Areas of zero size are part of the theory and are not there's nothing to do with the singularity. The spectrum of the area operator includes a minimal area, which is sort of roughly the Planck area, the square of the Planck length, but also zero, of course. So, and the question is the area of what, right? So, if I pick two, let's speak in terms of length, which is easier. If I pick 2 points, I can ask what is the length between the two. Okay, if I say, is there a grid with some length space, I can ask what is the space of that hypothetical grid. If I make a measurement of a diffusion of a particle by something, the diffusion number is measured in terms of area. So that's another. So loop quantum gravity says that when you measure something, you get an eigenvalue which can be zero, or can be 1 Planck area, or 2 Planck areas, or whatever. This is perfectly compatible with the fact that, let me put it this way, from the point of view of a photon, it's a very imaginative language, who's traveling a distance from a different galaxy to us, it is like the minimal area was zero. True. Okay. Is in a regime of curvature which is very small, and that particular sort of measurement, so to say, done by the proton is like the minimal area was zero. It's not. It's the minimal area of its own evolution, so to say. That's nothing to do with the singularity. Singularity, it's what happens at high curvature. For instance, the central black hole, or in early universe near the Big Bang, where the curvature the curvature space-time is very high, and what loop quantum gravity says is that there's a maximum curvature because somehow you imagine you have a little sphere, curvature is maximum because the sphere cannot be smaller than a Planck area. So therefore, the curvature cannot be larger than 1 over the Planck area, because small sphere means higher curvature. Mm-hmm. So the way the bound on the size of things come in to help with the singularities has nothing to do with what happened near flat space where there's light traveling.
Carlo, you know that Sabine just had a rebuttal or retort about this exact issue. And she said, and I quote, "If you quantize the angular momentum operator, the spectrum of the eigenvalues is discrete, and that doesn't violate rotational invariance. Carlo claims that it works similarly in loop quantum gravity with Lorentz invariance, but it doesn't. If you calculate the expectation value of the angular momentum operator, it will respect rotational symmetry, yes. However, that's because its eigenvalues are both positive and negative, allowing it to average to zero. In contrast, the eigenvalues of the area operator in loop quantum gravity are all positive and have a lower bound. Consequently, the expectation value for the area in loop quantum gravity is bounded from below, and it can't transform under the Lorentz group. This is a mathematical fact. Of course, Carlo knows this. Everyone who works on this stuff knows it. They just repeat this angular momentum story because it sounds superficially plausible if you don't know anything about quantum physics. Now, you might say, all right, the area can't transform under Lorentz transformation. Maybe there's some quantum stuff going on. Some weird things happen. Yes, actually, Carlo and Simone mentioned that in their paper. That's also why some people in loop quantum gravity suggested there ought to be deviations from Lorentz invariance. I tried to tell them this, but they didn't want to hear that. So, what should we hear?
Yeah. It's a technical misunderstanding. Sabine has an argument, and yeah, I think I understand where is the misunderstanding here. She heard many times there is a minimal eigenvalue of the area, and is a sort of Planck area squared, the Planck area, the Planck length square, a Planck area. This is what is said usually. It's not said correctly, obviously. I mean, the minimal eigenvalue is 0. It's a minimal non-zero eigenvalue, which is a Planck area. So in other words, what loop quantum gravity predicts is that there's a 0 eigenvalue, and then the next one, it's at finite distance.
Yes.
So you cannot get any eigenvalues smaller than the minimal and non-zero.
Sure, there's a gap.
There is a gap. But somehow Sabine misunderstood that for some reason, maybe because in some popularization articles or books was not said precisely. So she thought that there is no 0 eigenvalue. And therefore, if there was no 0 eigenvalue, she would be correct, and sort of complaining, wait a minute, you cannot Lorentz transform the mean value of the area arbitrarily small, which is what is needed for Lorentz invariance, if there wasn't a 0 eigenvalue. But there is a 0 eigenvalue. So I think maybe she never read the actual papers with the quantization of the area. What makes the loop quantum gravity finite, no ultraviolet divergences, is not that any possible area, it's always bigger than the Planck area. It's that any possible non-zero area, it's bigger than that. Is there a gap? So once this is clarified, her argument disappeared, and she was very nervous. I think she couldn't. She had a wrong idea in her mind that there was no 0 eigenvalue. That's made her. She should have perhaps asked the experts before going publicly with an argument based on a wrong assumption.
So this argument of a non-zero expectation value, does it not still apply if you have 0 and then positive values and you average that? Wouldn't it still be non-zero?
No. The average can be as small as you want. That's the point. You can continuously make the average as small as you want, including 0. I mean, 0 is it's a possibility. If you an area becomes arbitrarily small if you look from a arbitrarily boosted frame.
Mm-hmm.
So that's required by Lorentz invariance. So can we make it arbitrarily small? Of course, we can make it 0. Okay. In other words, the quantum state can rotate from maximum probability for finite eigenvalue to probability increasing probability to zero eigenvalue. And that's exactly what happened under a Lorentz transformation of an eigenstate of the area. It transforms in a linear combination of the other. If you go all the way through to the end, you get just to zero.
So you can Lorentz boost it below the Planck length squared?
Oh yeah. The difference here is the difference between expectation value and eigenvalue, right? So quantum mechanics says if you make one measurement of one quantity, just one, you can only get an eigenvalue. That's what quantum mechanics says.
Mm-hmm.
The
expectation value is the average between them. So electron is spin up and spin down, but technically its expectation value is zero then, but there's no spin zero electron?
It depends on the state. I mean, this a single atom, if I give you an atom, you can it can be in a configuration such that you see necessarily with suppose it's a spin one thing. There are three possibilities. Spin can be up, down, or zero.
Mm-hmm.
Okay, so now suppose you see it with spin up. Okay, all right. So now you rotate your head. Okay. And classically, the component of the spin in that direction would be zero because so you continuously rotate the component in zero from 1 to 0. Now, if you measure various types, you rotate the atom, you don't get something in between. Okay, suppose you rotate by half, or 45 degrees. You make a measurement. Then quantum mechanics says you have a half probability of measuring still 1 and a half probability of measuring 0. So the average transform continuously, but what you measure in one shot, it depend on the probabilities and its expectation value. So for consistency, you want expectation values to be able to change continuously when you make continuous rotation or continuous boost transformation. And that's okay because there are probabilities. There's nothing really mysterious. It's just quantum mechanics 101. It's not some deep, profoundly quantum stuff.
I see.
Right. So Sabine somehow was confused because she was saying, but you cannot go smaller than the minimal area if there's nothing else you can go to. Okay? Because she forgot that there is the area operator has also the zero eigenvalue. In fact, the eigenvalues of the area operator are given by the square root of j plus 1, where j is a half integer. So it can be 0, 1/2, 1, so this discrete spectrum times 8h bar g pi. And j can be 0. If j is 0, the area is 0. It's in the formula for the eigenvalue of the area, which is in all the papers or the books.
Does this whole brouhaha about loop quantum gravity being either testable or the expectation is not zero, etc., does this frustrate you?
No, I mean, it's not. Loop quantum gravity is not testable. It's my last paper, which was published on Physical Review Letter a couple of weeks ago, by myself, Alejandro Perez and Mario Christodoulou, respectively in Vienna and in Marseille. It's an idea for a possible test of loop quantum gravity. The others are published. So it's not because one particular proposal of testing it
exactly
did not materialize, then therefore the theory is untestable. No, I mean, it would be silly. If you cannot test the theory in a certain manner, it doesn't mean that the theory is untestable. And in fact, there are many other ideas of how to test it. Unfortunately, as we all know, no theory of quantum gravity for the moment has obtained a positive confirmation, a corroboration. Otherwise, we would, claim Nobel Prizes and be happy and celebrate. And we hope so. These theories are tentative theories. Loop quantum gravity, string theories, the others are ideas of how the world could be. And that's what science should do. I mean, should try to find possible theories. I think it's remarkable that after many years we have at least some candidate theory of quantum gravity. It's not true anymore that we know nothing about. We don't know how the world could be compatible with generativity and quantum mechanics. The world could be like loop quantum gravity, as far as we know. Is it? Oh, before believing it, we need the corroboration. We haven't got it. We're working. This Lorentz transformation stuff was one attempt 15 years ago, 20 years ago. There have been others with cosmological observations, now with dark matter, measuring Planck scale things. We hope that at some point some of these possibilities will be confirmed.
What's the reaction been like in the community about this recent fuss over the Chinese experiment and then the subsequent popular science articles about it? Or not articles, but sometimes even videos.
About in the community, with respect to the experiment, no, I think it was not even discussed because the large majority of the community, almost all the community, was already convinced that that effect should not happen. So it was not a surprise. Okay. In fact, I don't remember a colleague of mine pointing to this experimental thing. It's just the tension was not at all on those Lorentz violations. The tension was on cosmology, on dark matter, on black holes, on other stuff. So, and the fuss as you say, in the popularization things. Look, I got some people writing to me saying, "Oh, come on, look what these people what they're writing. Why don't they actually read the papers instead of commenting a priori?" I don't know. I definitely don't want to be negative or anything. It's great that there is popularization. It's great that, but I think there are different styles of doing popularization. There is a style in which you give opportunity to talk, you listen, you make comment, you try to simplify. There's also style in which the popularizers want to put themselves as judges of what is going on. And that's, I don't think, is very useful.
As you know, on Theories of Everything, we delve into some of the most reality-spiraling concepts from theoretical physics and consciousness to AI and emerging technologies. To stay informed in an ever-evolving landscape, I see The Economist as a wellspring of insightful analysis and in-depth reporting on the exact topics explored here, and even more. The Economist's commitment to rigorous journalism means you get a clear picture of the world's most significant developments, whether it's the latest in scientific innovation or the shifting tectonic plates of global politics. The Economist provides comprehensive coverage that goes beyond the headlines. What sets The Economist apart is their ability to make complex issues accessible and engaging, much like we strive to do in this podcast. If you're passionate about expanding your knowledge and gaining a deeper understanding of the forces that shape our world, then I highly recommend subscribing to The Economist. It's an investment into intellectual growth, one that you won't regret. As a listener of TOE, you get a special 20% off discount. Now you can enjoy The Economist and all it has to offer for less. Head over to their website, www.economist.com/TOE, T-O-E, to get started. Thanks for tuning in, and now back to our explorations of the mysteries of the universe.
In which the popularizers want to put themselves as judges of what is going on, and that's, I don't think, is very useful.
Okay, speaking of black holes, what is the firewall? What is the information paradox? And what does loop quantum gravity say about those two?
Okay, so we know that black holes are there. We have pictures of them. And we are all convinced, all theoreticians, or almost all, convinced that there is this strange phenomenon, which is Hawking evaporation. Hawking evaporation is a phenomenon for which if you take a black hole and you let it stay there isolated, you don't touch for a long time, it becomes smaller and smaller and smaller and smaller and smaller and smaller. And
I didn't know almost all. We can talk about that after. Who doesn't believe in Hawking radiation?
Oh, okay. No, that's okay. But the large majority, what I'm saying is that both sides of a disagreement, which I'm going to tell you in a moment, agree that
I see. Okay.
That the Hawking evaporation happens. Now, what we don't know, and what people have different opinions about, is what happened at the end of the evaporation. There is a part of the community to which I belong, which is mostly made by relativists or loop quantum gravity people or this kind of, that thinks that at the end of the evaporation, you're in a deep quantum gravity regime because the black hole is very small at this point. And black hole doesn't mean, a small black hole doesn't mean that you're close to non-quantum. It means you're very quantum because you have a very high curvature. That was what I was saying before. The horizon is super curved. And just around it, the curvature is Planckian. So you're in a deep quantum gravity regime. So what people expect in my community is that something quantum happens at that point. The other part of the community, which is mostly in the string world, that's another case in which there is a string loop, or sort of a stringy world or loopy world, because it's much larger than the people doing actual theories, expect is that when the black hole is very small, poof, disappears. There's nothing. Nothing at all there. Now, why I consider that implausible? Because if you look at the geometry, when the horizon becomes very small, inside is still very big. There's a huge stuff inside. It's not that's gravity, right? In a small sphere, you can fit a big volume because space-time is curved. So you can imagine a flat thing with a small throat and then a huge bottle inside, or a huge pit inside. So that's a black hole. It's very small, but this long thing inside. So what I expect to happen is that there's a quantum transition that allows this internal part to come out. So all the information inside slowly can come out. And so what I expect to happen is that a small black hole, it's remaining, is becoming a remnant. It's remaining small from outside for a very long period, and becomes what is called a white hole, which is a hole from which the inside can come out. So the information inside can come out. Now, if you instead believe that the black hole is disappearing, you're led to believe that the information inside is lost or has to come out somehow before. And a lot of people in the string world got convinced that the information has to come out before a certain number of arguments. And so I've devised all sort of hypothetical phenomena that bring information out before. So you have a black hole, things fall inside, information inside. It should come out before the end of the evaporation, they think. If you believe that things come out outside, you also believe that when the black hole is small, the information inside, it cannot be large. Okay? So I think that you can have a small black hole with a huge information inside. Okay? And people say, no, because a small thing cannot hold a lot of information, which is true of flat space, but it's not true of curved space. Okay? So they have this strong holographic hypothesis, as they call them, or the central dogma, as Juan Maldacena calls it, correctly so, because a dogma is not something we know about nature. It's something we think.
Interesting.
They think could be added to nature. That a small black hole doesn't have information anymore, so when it disappeared, there's no information there, everything has come out before. So they have a puzzle. How does information come out? And that's the so-called information, black hole information puzzle. And they have ways to describe it and to solve it, which basically amount to not believing quantum field theory, to thinking that quantum field theory goes wrong in some strange, mysterious way. The firewall that you mentioned.
Firewall.
Yeah, the firewall that you mentioned, it's related to that. So if that happened near the horizon, it's like there is a super high energy, so you get sort of burned if you go there. my part of the community, which include myself and many people who look quantum gravity and many people also for classical general relativity, do not buy this story and think that information comes in, stays in all the way through the evaporation, and then comes out slowly from remnants. And I, colleagues, are trying to use this idea to see if this remnant can be observed. And my last physical review letter is exactly an attempt to describe a device that could measure, in principle, these remnants.
Now, when I speak to people on this channel, often when they propose some new particle or something akin to a remnant, they'll say, and that could be dark matter. In your case, do you also think it could be dark matter?
Yes, of course, because dark matter is probably the biggest, I would even say almost the only, a concrete, mysterious thing that doesn't fit with our basic equations, right?
Are the remnants so small that they're like neutrinos and could be going through us millions or trillions of times a second and we wouldn't feel them? Are they akin to that, or no? We would definitely feel them if they went through us.
No, it's the first. We would not feel them. Not because they're small. Well, they are small. They are super small. But because they only interact gravitationally.
Ah.
So it would not interact electromagnetically. It would not interact with a strong force. It would not interact with a weak force. So they could go through you, and the effect through you would be just like the Newtonian attraction of a hair moving next to you, which is absolutely minimal.
I thought that they're also exporting something like radiation, but extremely slowly from the information content on the inside.
Yeah, they're also losing the information outside, but that's extremely slowly, extremely low energy, very, very long wavelength. So we looked into that. We have some paper about that. I don't think that would be measurable at present. At least I couldn't come out with any way of measuring that radiation at present. While the passage of these things, if dark matter is these things, and it could, because dark matter, as far as we know, interact only gravitationally, and these things interact only gravitationally. So they're good candidate of dark matter. Of course, they're one of the 10, as you say, they're one of the 20 candidates of dark matter around. But we don't know what's dark matter. So, and I like these candidates because they don't require extra physics in the sense it's not a new particle, it's not a new field, it's just general relativity and quantum mechanics together.
Right.
So general relativity and quantum mechanics, you make a black hole, weight becomes very small, becomes one of these remnants, so you have plenty of this. So if in the history of the universe, and that has to be understood, somehow many of these things were produced, we could have a lot of these things around, they would behave like dark matter.
So Neil Turok believes that they're right-handed neutrinos.
That's another of the hypotheses about dark matter. It's beautiful, right? We are in this situation. It's much more interesting that thinking that we have the standard modern general relativity and in principle everything derived from there. No, we have something that doesn't seem to derive from there. So we have all sorts of hypotheses. It's an exciting situation in fundamental science.
The last time when we spoke over email, I told you about the Yoneda lemma in category theory because I saw it as relating to relational quantum mechanics. Because in the Yoneda lemma, it says that an object in category theory is fully understood in terms of its relationships, so its morphisms, with all other objects, as long as you're in something called a locally small category. In other words, some people use this to say that an object is completely defined by its relations to other objects. That you can either define the relations to objects or you can define the object itself. It's dual. It's exactly the same. And then that had me thinking, I wonder if that has implications for relational quantum mechanics.
Yeah, the answer is I don't know. I mean, what you characterize as the main idea behind this theorem is exactly the idea of relational quantum mechanics, right? So an object is defined by all the relations that has around it. So if you want to think as an object by itself, there's no meaning. the object by itself.
Mm-hmm.
And category theory, it's certainly a natural mathematical language for talking about these things, because in a sense, it's a category theory. It's born with this idea that it's a structure, the largest structure that determines what we're talking about. But I am not competent enough to use category theory. Maybe I should. And in fact, people have been telling me, why don't you? Category theory is, people get in love with it when they study it.
Oh, yeah.
And because obviously there's a great beauty there, but it's complicated to get into that, because it's not just a mathematical theory, it's a mind frame, I would say. And I'm not sure the extent in which it could be useful, or could just or is necessary for articulating the idea that underpinning relational quantum mechanics, but also much more trivially and simply, I'm afraid it would make people stay away from quantum mechanics articulated that way. I think there have been some people in France that looked into that, but I don't remember right now. I wish I could be smarter and know more things and add this to the thing I'm doing.
What else is exciting is consciousness. And many physicists don't talk about consciousness. You think plenty about it. You have relational quantum mechanics, which says something about consciousness, if I'm not mistaken. But either way, I want to know, in your view, what observes the observer?
Relational quantum mechanics says something about consciousness very indirectly. So it's not a theory that leads to consciousness. I don't think that consciousness has anything to do with quantum theory. But indirectly, yes, because relational quantum mechanics tell us that the best way to think about the world is to describe it in terms of how things affect one another. So you don't describe how things is, you define how a thing affects another object. And that makes, what's the problem of consciousness? The problem of consciousness is that we think there are two things. One is matter, atoms, molecules, stones. And one is my spirit, my thinking brain, okay? And if you start from that, it's very hard to think that the two are of the same kind. But I think that both ideas are very naive. There's no my spirit, my soul, my thinking, my observing thing. I am just a piece of nature like anything else.
Uh-huh.
And I follow laws of physics, and my brain is very complicated. And the complication of my ideas is the complication of the neurons of my brain. It's just another way of describing things. Matter also is not so naive, like sort of a very naive materialism would suggest. Matter is not just little stones or molecules bouncing around, because we know quantum mechanics. Quantum mechanics tell us that it's more complicated. Nature is more complicated. Nature is about how things affect one another. An electron is not a stone. It's something. It's real, but it's only real as far as interact with something else. So if you think matter in that way, my brain interacting with the rest, it's doing the same thing that the rest of universes does. Species interacting with species. Now, this does not mean that the universe is mental, because my way of being or your way of being, it depends on the specific of the brain. We are very special pieces of of nature, but we're special just because we're complicated and all these things happening. So I think that if we start from a fundamental sort of philosophy,
Yeah.
where we describe the universe in the way as a collection of things, each one of that can be described in terms of the others, and how things have information about one another, how things interact one another. We have a unified way and a unified language in which both the strange thing behavior that we call consciousness, nobody knows what they mean by consciousness. It's just how we are. And the way stones and planets and plants and the universe are described in the same language. And then the separation vanishes, I believe. So I believe that the separation should vanish and will vanish in the same manner in which some decades ago people thought all living beings is completely different than non-living being. The biosphere is something totally different. Well, it's not totally different. It's just a special set of processes, but just physical process, chemical process. We call biological process a peculiar kind of chemical process. So I think our thinking is just one of the many things of the universe, which is very complicated and we understand it very little.
And in your view, because from the surface, it sounds like it's suggesting consciousness is fundamental. If the relations are fundamental, somehow consciousness is related to the relations.
No.
It sounds like that. How can it be that there's an experience attached to something that's not conscious?
I think the relations are fundamental, but consciousness, what we call consciousness, is not at all. The difference is that I need the notion of relation to describe everything. But when I think about consciousness, I mean, I'm describing you. You have memories, you have language, you have anticipation of the future, you have a brain that does a lot of very peculiar things like keep remembering and yes.
To say the least.
Exactly. And some of this, one by one, some of these things are comprehensible, right? It's, for instance, how you take decisions. Well, you have information and you elaborate, you do things. And my computer takes decision when it plays chess with me in a similar way. So that part is in common. How you look around. Well,
the experience part, though, the part that it feels like something.
Yeah, the point is that when you try to pinpoint what exactly do we mean by that thing which is different, when we try to say it precisely, we can't. We use vague words, and these vague words are just saying that we don't know what you're talking about. So I don't think there is anything special in experience by itself. It's just one of the aspects of the world which is not very different, which is a much more complicated version of that stone which is falling on the other stone and affecting it. Much more complicated. And this complication, this additional complication, is what makes it so rich that we... I don't think there's anything different in me explaining how that stone is affected by another stone, and me trying to understand how you, Curt, are affected by talking with me. It's just, in one case it's easy, in one case it's super complicated. The difference is just the level of complications. And what we call consciousness is this extra complication.
So you believe that a stone is feeling something when it's hitting another stone?
No, because feel is I believe that its behavior is affected by the other one, and what the right language for describing what is going on is a relation between the two. And feeling is related to emotion, to things that you have when you have neurons that fire up and say, "Oh, I'm feeling something." Feeling is a name we give to something that happens in us, and it's a proper name. It's a good name, but we don't use this name for a stone. It would make no sense.
If you had 10 graduate students and you could delegate them to the most tractable, promising direction for either relational quantum mechanics or loop quantum gravity, what task would you set them on?
Sitting down and trying seriously to compute the transition amplitude of a black hole at the end of the evaporation.
So the remnant black hole, when it finishes being a remnant?
Yeah. You see, my understanding of loop quantum gravity is that more or less it's a theory. It's a good theory. It's a consistent, coherent theory. We don't understand it well. It's hard to do calculation. We're not sure how to define it. I mean, we're fighting about us in loop quantum gravity. This version is a bit better than yours, of course. And there are things which have not been proven yet.
Right.
All sorts of troubles. But it's a theory. It's a consistent theory of quantum gravity. What we don't know is whether it's correct theory for describing the world or not. So I would tell the students, look, work on the application. Try to apply the theory to concrete phenomena. There are many concrete phenomena, early universe. I mean, but the end of the evaporation seems to me, which is the same problem as the singularity. Somehow the singularity is connected to the end of the evaporation. There are a number of papers who try to do this calculation, but they're very, very primitive, little. It has not been explored yet. There is a mathematics which is available. It's a beautiful physical problem. It's out there. We see the black holes. Okay, what's going to happen to them in the future? Most likely, I mean, unless there's people you hinted to before, right? Most likely they are going to evaporate, and then what? So we're asking some concrete problem, and if it happened to be connected to dark matter, it would be fabulous, because we could, then there would be a lot of these remnants and we could check them. So it seems to me that that's a possible opportunity for doing for using quantum gravity, not just for talking about abstract possibilities, but for studying something happens in nature.
Have you thought much about how it came to be that loop quantum gravity is the second place in terms of theoretical physics? What I mean to say is that it's seen from the outside and sometimes from the inside that string theory is the big dog, and that its competitor is loop quantum gravity. Like whenever people are talking about what is the theory of everything or a theory of quantum gravity, they say it's string or loop. Have you thought much about how did loop get to be on that stage and not something like asymptotic safety or Rogers twistor program or something else?
Yeah.
How did that come to be? There's plenty of thought about how string theory rose to prominence. Lee Smolin has some book, at least one book about that. And I'm curious about the sociology of player A and player B.
First of all, I think that the description you gave is it's true that people think in these terms in the science community as well. And what they actually are talking about, it's a scientific judgment, but it's also much more simply number of people working, right? I mean, as in total safety, there is a few people working. In the other attempt, the other possible direction to quantum gravity is just a small group of, one group or two groups, or loop quantum gravity is a large community. There are dozens of groups around the world. There are conferences, hundreds of people. Some do cosmology, some do black holes, some do mathematical physics, some do the covariant version of quantum gravity, some do canonical version of quantum gravity, and so on and so forth. So there's a world around that. And string theory, people who say they're doing string theory are more. And they're actually much more variety of things they're doing, because people try to say this. Some people say this doing string theory, even if it's vaguely related to string theory, what they're doing, right? There's a lot of development,
right?
And this is sort of a little bit self-sustaining because it's good to be part of a larger community. If you can connect to them, you're. So the description you gave does reflect the actual situation. The majority of the people interested in quantum gravity are in these two communities, strings and loops. How come? Historically, there is a clear track to that, which is the history of general relativity as a scientific research field. General relativity, of course, started with Einstein, who wrote the theory, general relativity, more than 100 years ago. And it was a very isolated group of people who were doing that for a long time, very few. Because there was not much to do. The theory had these three little successes: the perihelion of Mercury, the deflection of light by the sun, and somehow the redshift. And that's it. Nobody knew how to use it to anything useful. And that was for very long. And then at some point, it started becoming more and more useful. Application, technology, the GPS, astrophysics, cosmology started booming, and black holes, gravitational waves. So suddenly, general relativity became larger and larger and larger. But the people who come from general relativity were different people than those who were schooled in the particle physics. So those who did the standard model, Weinberg, all the and so there were two different communities. And when both communities started to be interested in the quantum gravity problem, which of course interests both, they took very different. They had different philosophies, different way of thinking, different mathematical tools that were used. And so this gave a big cultural difference. And then something happened in the 80s, which was, this is just sociology, history. Both theories got great results in the 80s. It was a moment of surprise. But yeah, theoretical results. In the 80s. That's the moment in which people got excited. But precisely because it was a great moment of excitement in both parts, few people looked at the other one, right? So
why?
Well, because you say, I'm in a theory that seemed to be working. And then you just focus on it while you want to look at the others. It seemed to be working. You just go ahead. That's, for instance, when string theory sort of realized that there is an almost unique string theory. It was a great result with the anomaly. And in loop quantum gravity, there was a solution of Wheeler-DeWitt equations. Wow, incredible! We have a solution of Wheeler-DeWitt equations. So the two communities ignored one another for a while, and they had so different mathematical methods, assumptions, that every attempt to communicate, except few people, there are some people, at least one is one, who try to learn both things. I try to learn string theory, but somehow always as a mature, not as professional string theorist. And it's really, you see, if you're string theorist, you think that energy, it's major thing. Momentum, energy momentum it's a fundamental thing in terms of thing to think. If you come from general relativity, energy momentum is just not defined in general. It cannot be fundamental because in general there is no energy momentum of gravity itself, which can be defined in any decent way. There is only energy momentum of matter, but not of gravity itself, except in specific cases. So what you consider your basic conceptual tool for thinking about reality in one camp were not in the other camp. So there was this long separation, and this a little bit is still there. It's okay. I think the debate is still going on, and we do have hopes of. There were both directions, of course. There were hopes of finding something that could help. Not much. or almost nothing directly observational so far has come in. Some very disappointing thing has happened. I mean, supersymmetry was very disappointing. If it had happened, I suppose many people would say, well, those people have a point. I mean, they seem to be...
Well, was it disappointing to you? Supersymmetry is not in loop quantum gravity.
Oh, no. String theory. No. The non-discovery of supersymmetry was great for us because the disappointment of your competitor is just by that.
You looked personally disappointed though.
I was not personally disappointed. I was just happy, going around happy and smiling every time. Hey, you see, you were all waiting for supersymmetry. I told you that there was story. So I didn't find disappointing. But then there's also another difference. And that has to do with the name of your show, Curt.
Sorry.
No.
I'll change it to effective field theory.
Keep it. Of course, you should keep it because it's a great idea. The hope of finding a theory of everything, but loop quantum gravity never considered it its own problem. Loop quantum gravity, in a sense, that's the big difference is loop quantum gravity, in a sense, is much more ambitious. Okay, we are going to understand how to do physics without space, without time. Really, space is not like you who have to go observe over the infinity where you know is space and time. We are smarter because we face the big problem directly. I mean, quantum space and quantum time. But on the other hand, loop quantum gravity is super humble compared to the ambition of string theory. Because loop quantum gravity is not a final theory of everything. It's not a unification of all the forces. It's not something which pretend to be an arrival point for theoretical physics. It's a very humble enterprise, which is, we know the gravitational interaction. What happens when you cannot disregard quantum mechanics in this gravitational interaction? So what happened inside the black holes? That's the only, or what happened at Big Bang? And then, but what is an electron? Why there are 16 particles? I don't know. That's for the future.
Mm-hmm. I see it two ways when it comes to the humility argument, because it could be that we just need to take one step forward, but it could be there's some chasm and you actually need to jump. And anytime you're taking a step, you're just going to fall. You're like, well, look, I'm super humble. You all are just jumping into the void. Yeah, but you need to jump further.
Yeah. No, of course, we don't know. I was, you see, I grew up in the 70s. I went to school, to university of physics in the 70s. At the time, the big problem was the strong interactions. Right? The strong interaction was a mystery. Somehow the weak interaction, there was already the attempt to Weinberg-Salam, what we call today the theory of weak interaction, SU2 cross U1. But the strong interaction were very mysterious. And there was a large number of particles that were found, the zoo of, I was very confused. And the strong interaction was strong. Namely, you expect the perturbation theory to fall. And what I got from my teachers at the time, the mantra that everybody was saying, my teachers were all wrong. Mm-hmm. They were saying, look, quantum field theory has a problem because of the infinities, the renormalization. Quantum field theory is shit because, what is this renormalization business? It's not clear, which is... And the renormalization problem comes because of perturbation theory. And the strong interaction, you cannot do perturbation theory. So obviously, there were people who were saying, the problem of understanding the strong interaction and the problem of understanding renormalization, getting rid of renormalization, must be the same problem. And therefore, the solution must be forget quantum field theory, find an alternative to quantum field theory, and this alternative to quantum field theory will not have renormalization problems and will make sense of the strong interaction. This is ideas, go back to Heisenberg, the S-matrix, people were working, bootstrap, a lot of stuff. So in other words, with two problems, clearly we should solve the two together. And what happened historically is that was wrong. Because Gross and Wilczek and everybody else, Gell-Mann, solved the strong interactions beautifully with a theory which is QCD. It's marvelous, one of the best theory we have, which still have all the problem with normalization, infinities, and is a quantum field theory. And they were a minority at the time. Wilczek and company, and Gross and Gell-Mann were a minority who were looking for a quantum field theoretical solution for the strong interaction. Most people were looking for a non-quantum field theoretical solution of strong interaction. So, of course, I mean, as Einstein said, same trick doesn't work twice. But I grew up with the idea that you can very well have two problems on the table and think, of course, they're connected. That's not true. You can solve one and the other tomorrow.
So speaking of David Gross, that conversation that you had with him 2 years ago or so, that's something that every aspiring physicist and every
thank you.
existing physicist should watch, because it shows string theory is the big boy, and it demonstrates that they don't even listen to their competitors. There was a part in the conversation where David was saying, you in loop quantum gravity, though you're the representative at that point, you can't even explain so-and-so. What was it? Fermions, putting fermions in loop quantum gravity. And you said, David, that's something that we solved 20 years ago. Something like that. Do you see this in the same way that I see it?
Yeah. It's yes, and it's a double problem. One problem is in communication. So a lot of people theory criticize loop quantum gravity, but criticize what loop quantum gravity was 20 years ago. This problem is open, but that was open 20 years ago. That's not the problem today. There are problems today. But also the second, it's more serious as well. I think we don't need to be experts of each other's theories, of course, because one cannot be expert of everything. But it's very useful for science, and science should go ahead by knowing what are at least the claims on both sides, right? So.
Like, it's one thing to have great results in your theory. It's another thing to say you're the only game in town. And it's another thing to say you're the only game in town while not looking at what other people are doing.
Yeah, I think you put it very clearly.
We'll end with, what are your hopes? What are you working toward? Other than this Princeton conference coming up for relational quantum mechanics, what are you working on and what do you hope to solve in the short run?
We talked about the black hole, what happened to the black hole at the end of the operation.
Right, the remnant, yeah.
Before talking to you, Curt, this morning, I was on Zoom with a colleague in Marseille, brilliant young professor, just got a faculty position. And we spent 3 hours this morning getting confused about how to think about this. This is a sort of tunneling process. So we're trying to understand which sense is a tunneling process. How do you a tunneling process, not in time but off space time in some sense. I would love to get some clarity there.
Yes.
And in fact, I wish I could concentrate more on there rather than doing all the various things that I'm doing at present. That's for me
What are the various things you're doing?
Well, I've written popular books, and I'm pressure of that. I get invitation. I do this philosophy thing. I am a bit too dispersive, and I want to focus more. You asked what would you like to focus on. I would like to focus on understanding that particular. It's a well-posed physical problem, right? That's the beauty of it. You have a black hole. They are there. They're out there. In fact, there's another way of putting this problem that I like. We see the black holes. We see the matter falling in, right? We see the spiraling, the accretion disk, as they call it. And we know, because we know general relativity, that matter, it's a spiraling and then going into the horizon. And we know general relativity, so it goes into what we call the singularity. what happened next to that matter? We have no idea. So it's a very concrete thing. It's a kid could come in and say, oh, there are all these holes in the sky and things falling in. Where does it go? The answer is we don't know. So, I mean, come on. We are scientists. We pretend to understand so well the universe, we should be able to answer this question. We have quantum mechanics. We have general relativity. We have all these ideas. We have the tools. That's what I would like to focus upon. What happens if you fall into a black hole?
What happens if you fall into a black hole? Like an observer, you want to know what happens to that person?
What happened to it's the same question for me. I mean, what happened to the matter that falls into the black hole, which is very much connected to what happened to the black hole at the end of the evaporation. See,
I see.
The magic of general relativity, the classical general relativity, that time is very flexible, right? Time can go, you can go from here to here, very long time, a very short time.
Yes.
Two people can separate and meet, and for one is a long time. So if you go into black hole, assuming that you're not squeezed, and if you go through the tunneling and you come out of the white hole, outside is a huge amount of time, but inside it's a very short time. So the information that falls into black hole very fast goes to the singularity or the non-singularity, this tunneling, and then very fast come out. But from the outside, it's a very, very long process in which you see the black hole evaporate and then stays and then things come out. So the problem of what happened to the matter inside is the same problem as what happened to the end of the evaporation.
Okay.
And that's the problem we would like to get some better understanding.
So in traditional general relativity, when something falls in, if you're an observer on the outside watching something fall in,
that's correct.
You don't actually see it cross inside. You see it accumulate at the boundary. And then you're saying, but at some point it does need to evaporate if we're to make it consistent with quantum mechanics.
Precisely.
Then what happens?
Precisely so.
So speaking of boundary, Nima Arkhani Hamed said, any quantum gravity needs to tell us what happens at the boundary of space-time. What's meant by that? Do you agree?
Yeah. I know what they think. And I mean, last time I was playing some physics, I talked with Nima about that. I agree to some version of this statement, but not to the version that he means. The way we do quantum gravity in loop quantum gravity demands to know what happened at the boundary, but the boundary can be in a finite region. Okay, so I can do the following experiment. Suppose we had a super technology. I can take some matter, I squeeze it, I make a black hole, I weight it, I see what comes out. Okay, all this happens in my room from some initial time to some final time. So I need to know what was the beginning, what happened on the walls, what at the end, in a finite time. That's true. I need to know the boundary of the process to see the probability of, given the initial, what, okay. So that's correct. But Nima and with him, the Princeton people, I'm not sure the West Coast people, string theorists, agree. They think that the boundary has to be at infinity, that I can only go at infinite distance and look at the boundary there. And I'm not convinced. So they have argument to say that I cannot be in the middle of space-time and measure quantum gravity measurement there. And those arguments I don't buy. I think mathematically they get in trouble if they try to see what happens if I make measurement at finite distance, but they are in trouble because they assume a continuous space-time, which is one of the assumptions. Well, there's no continuous space-time. That's the point. They have some infinities that they are struggling with, but these infinities are the infinities that come from forgetting that there is this quantum discreteness in space-time.
What's meant by infinity if the universe is infinite? So how do you take the border of infinity?
Well, that's how they think about it.
Do you mean infinitely away from some region? Like you're defining some region, then you say infinitely away from that?
Yes. That's the way they think about it, and Nima in particular. So they think there's some process here, but the only way to describe it is that I have to go at a very large distance, and at very large distance.
I see. Because technically speaking, you're at the infinite boundary of something else, if the universe is infinite.
You're right. No, what I think is that the way of describing a quantum gravity phenomena is to be at infinite distance from it, and sort of for a very long time see what happened. And I think this strong requirement that they give, for them is easier because at the infinite distance you assume the space-time is flat, right? So they put the observable at what they call a symptotic infinity, assuming that their space-time is flat. So they're home. They have energy, their momentum, they're all the tools of a flat space-time.
Mm-hmm.
While if you're yourself in a region, if the boundary is itself in a region where it's curved geometry or strong gravity, you don't have those tools. So no surprise that they have difficulties of working at finite distance. I think that it's work at finite distance simplifies the problem. So I want to understand what happened to a black hole in a sense by surrounding the black hole in a small box and see that's my problem is just a small box, not the entire universe.
Carlo, I appreciate that of the 20 different items you could focus on, that you're dispersed. And I appreciate that you've spent 2 hours or so focused on myself in this conversation. That's incredibly flattering. And the audience appreciates it as well. Thank you so much.
Thank you, Curt. Again, it was wonderful, this conversation. I very much appreciate it.
New update. Started a Substack. Writings on there are currently about language and ill-defined concepts, as well as some other mathematical details. Much more being written there. This is content that isn't anywhere else. It's not on Theories of Everything. It's not on Patreon. Also, full transcripts will be placed there at some point in the future. Several people ask me, "Hey Curt, you've spoken to so many people in the fields of theoretical physics, philosophy, and consciousness. What are your thoughts?" While I remain impartial in interviews, this Substack is a way to peer into my present deliberations on these topics. Also, thank you to our partner, The Economist. Firstly, thank you for watching. Thank you for listening. There's now a website, curtjaimungal.org, and that has a mailing list. The reason being that large platforms like YouTube, like Patreon, they can disable you for whatever reason, whenever they like. That's just part of the terms of service. Now, a direct mailing list ensures that I have an untrammeled communication with you. Plus, soon I'll be releasing a one-page PDF of my top 10 toes. It's not as Quentin Tarantino as it sounds like. Secondly, if you haven't subscribed or clicked that like button, now is the time to do so. Why? Because each subscribe, each like helps YouTube push this content to more people like yourself. Plus, it helps out Curt directly, aka me. I also found out last year that external links count plenty toward the algorithm, which means that whenever you share on Twitter, say on Facebook or even on Reddit, etc., it shows YouTube, hey, people are talking about this content outside of YouTube, which in turn greatly aids the distribution on YouTube. Thirdly, there's a remarkably active Discord and subreddit for Theories of Everything, where people explicate toes, they disagree respectfully about theories, and build as a community our own toe. Links to both are in the description. Fourthly, you should know this podcast is on iTunes, it's on Spotify, it's on all of the audio platforms. All you have to do is type in Theories of Everything and you'll find it. Personally, I gain from rewatching lectures and podcasts. I also read in the comments that, hey, toe listeners also gain from replaying. So how about instead you re-listen on those platforms like iTunes, Spotify, Google Podcasts, whichever podcast catcher you use. And finally, if you'd like to support more conversations like this, more content like this, then do consider visiting patreon.com/CurtJaimungal and donating with whatever you like. There's also PayPal, there's also crypto, There's also just joining on YouTube. Again, keep in mind, it's support from the sponsors and you that allow me to work on TOE full time. You also get early access to ad-free episodes, whether it's audio or video. It's audio in the case of Patreon, video in the case of YouTube. For instance, this episode that you're listening to right now was released a few days earlier. Every dollar helps far more than you think. Either way, your viewership is generosity enough. Thank you so much.